First of all, I would like to welcome all of you from all over the world for this EC series of Game Changers seminars or webinars. Today we are starting a new series which is called Space Environmental Hazards Mitigation and Prediction, in which we will not only talk about space weather, we will have a closer look at the connection between the space environment, the physical properties of our space environment, and the more societal user impacts of the hazards. And in this series of 9 presentations, we will visit different aspects. Not all of them are well known. Some of them will deal with GPS reception, the viewpoint of pilots in civil aviation. And well, today it's a pleasure to welcome Ilya Usoskin, because he'll be talking about a topic that has received a lot of attention, which is about extreme events, extreme solar events. I forgot to present myself. I'm Eruptive. I'll be your host for this series. Just a few words about Ilya Usoskin. So he's currently full professor at the University of Oulu in Finland. He graduated from the Leningrad Polytechnics in 1988 and worked at the Yov Physical Technical Institute in St. Petersburg. Went in Italy for some time before moving to Oulu, where he became responsible for the cosmic ray station. And he became full professor in 2012. So Ilya has a very versatile profile, I should say, because he's been working on cosmic ray physics, heliophysics, solar terrestrial physics, and also solar atmospheric physics. And he has played a key role in coining the word of space climate. And he received quite a few awards, including the Julius Bartos Award from the EGU in 2018. But I'll stop here, otherwise the list will be too long. So let me just specify for you who are listening, this presentation will be recorded. If you have questions, you can either use the chat or raise your hand, and we will address the questions at the end of the seminar. So with this, I think, Ilya, the floor is yours, and I'll let you start.
Thank you, Terry, and thank you for inviting me and giving the opportunity to talk about the very hot topic of extreme solar events, and thanks to EC2 for organizing this series of webinars. And I will be talking about extreme solar events, and whether they are black swans or dragon kings, I will explain a bit later what are this. And first, I will start from a little piece of poetry. Let me start today's performance with the name of God. Wait a second, hold for a moment, you're surprised. What? What you think and God of mine, they're not the same. He gives us all what we die. Helios his name. He is thought to be with smile, hiding in the cloud. But he can be quite hostile. Do we know how? And now we turn to the sun as our God. And here I show 2 examples of what we observe on a hostile sun. That's related to the Bastille Day events in mid-July of the year 2000, where there have been a flare on the sun and followed by a coronal mass ejection, as shown in the left and right hand side movies. What is important for us now is that after the flare and even more after the coronal mass ejection, we see white spots on the movies like snowflakes. These are charged energetic particles from the sun which hit the camera, and where they hit the CCD pixel, there is a white spot for a moment. And as you can see, these particles are quite numerous. This is one way to show that indeed after eruptive events on the sun, there are energetic particles in space, But of course, a camera is not an optimum instrument to study this kind of solar emission. And there are other ways to do it best, and that we proceed further. One of the things to study energetic particle is, of course, direct measurements by spaceborne or ground-based instrumentation. But the time of our direct scientific era is quite short. So for spaceborne instrumentation, it's few decades, and for ground-based instrumentation, a little bit longer, but also about 70 years. But if we can go further into the past and study solar events producing solar energetic particles before the era of direct measurement, we still have very good instrumentation thanks to the Mother Nature, and it's based on terrestrial cosmogenic isotopes, as illustrated very schematically in this plot. Let us assume on the left-hand side is shown the ground of the Earth atmosphere, and let us consider that at some moment T1, two energetic particles, cosmic ray 1 and cosmic ray 2, with different energy, hit the Earth atmosphere. Since their energy is quite high and atmosphere is very thick, we have roughly 1 kilogram of air per each square centimeter above us. This is very high thickness. Cosmic rays will almost unavoidably collide with one of nuclei of atmospheric gases, producing in particular nuclear reactions, and the number of secondaries as shown schematically in this plot by stars, which are nuclear reactions, and arrows are secondary products. Highly energetic particle can produce a cascade of such nuclear reaction, so that in each reaction there is a secondary nucleonic product, which can be different types. In particular, here is shown isotope carbon-14, known as radiocarbon. It's radioactive isotope of carbon, very commonly used for archaeology, for dating, and also for study of solar variability in the past. So this radiocarbon can be produced quite close to the ground and absorbed by living tree, for instance, which doesn't care what isotope of carbon it is. It just uses carbon from the atmosphere to build its body. Another particle, cosmic ray 2, with smaller energy, cannot produce the full cascade, but still maybe 1 or 2 nuclear collision, and producing in a similar way radiocarbon higher in the atmosphere. But due to the atmospheric circulation, this radiocarbon will be also brought down to the ground and used by the tree to build its body during the same time, T1, so that both of them will be stored in a tree ring related to that particular time. Let us now consider a similar pair of particles, more energetic and less energetic, entering the atmosphere at time T2, which is many years after the T1. The story is the same. 2 isotopes are produced, and they are stored in another tree of this, on another ring of the same tree, corresponding to the year T2. So roughly we have a time resolution. So at each, measuring the amount of radiocarbon in each of these 3 rings, We can estimate the flux of cosmic rays entering the Earth atmosphere during that year on average. And since the recording is done by nature in the same way and measured nowadays in modern laboratory, basically we do not have degradation of the quality of data when going into the past, at least in a reasonable time, hundreds and thousands of years. Thus, we can reconstruct the flux of energetic particles impinging on the Earth atmosphere as function of time. And for such studies, indeed, several cosmogenic isotopes have been used. One, as I showed right now, is radiocarbon, which is produced by neutron capture on nitrogen and measured in 3 rings, typically, which are independently dated by the dendrochronology. Its half-life time is around 5,700 years, but there are also other isotopes, cosmogenic isotopes, beryllium-10, which is produced by spallation of oxygen and nitrogen, has a half-life time of more than 1 million years, and measured typically in polar ice cores, which can be also independently dated, so that we independently know the date at which flux of energetic particles has been measured. As I said previously, we do have a temporal resolution for cosmogenic isotope, but for one isotope, for instance, for radiocarbon, we don't have any spectral resolution. So we cannot distinguish between high and low energy of an incoming particle. However, if we use several isotopes of that kind, we can play with their response function or production function, so that some isotopes, as shown here, for instance, chlorine 36 is more sensitive to lower energy cosmic rays, while radiocarbon and beryllium 10 isotopes are sensitive to slightly higher energy of cosmic rays. And in the bottom panel, I showed the sensitivity curve of chlorine, which is sensitive mostly to the energy of a few tenths of mega electron volts, radiocarbon and beryllium to energy of around 200 mega electron volts. And for comparison, the gray curve shows the response function of a typical neutron monitor, which is used to measure cosmic rays on the ground, which has an effective energy for solar energetic particles of around 1 gigaelectron volt. So if we have several isotopes, we can very roughly estimate the energy spectrum, as will be shown a bit later. That was an introduction, and now we will speak about what we call extreme events. They have been discovered 10 years ago in 2012 with the pioneer work of a Japanese group by Fusami and co-workers, who discovered that there have been a spike in the radiocarbon in 3 rings corresponding to the year 775 AD. There have been several measurements and all confirmed that there is a spike, which means that the flux of energetic particles have been greatly enhanced during the year actually 774, because 1 year it takes for the redistribution of radiocarbon in the terrestrial system. Then very soon it has been confirmed that the same spike exists also in beryllium-10 isotopes in both Antarctic and Greenland ice cores, as shown in the right-hand side of the of this slide. And here the red curve shows the measurements, and blue curve shows a model which agrees very well with the measurements. So it was indeed a very shorter than one year, probably shorter than few months, great increase of production of cosmogenic isotopes. Several hypotheses of this increase were proposed initially. The first idea proposed also by the discoverers of the event by Miyake et al. That it was probably in a nearby supernova, which produced a flux of gamma ray, which can also initiate cascade in the atmosphere and produce cosmogenic isotope. However, it was shown very soon that this idea doesn't work for several reasons. Because gamma rays can produce radiocarbon, but they almost do not produce beryllium-10, but beryllium-10 has been observed. Then there was very clear hemispheric symmetry between cosmogenic isotopes, while for a point source of gamma rays, we would expect to see more isotopes in one hemisphere with respect to the other. Then there were no known remnants of nearby supernova, which we would probably see. And the frequency of the event, I will tell that in a few moments. When it was a single event, it can be, you can speculate, but now we know several events of this kind. A similar proposition was put forward by some other group that it could have been gamma ray burst, but it was rejected based on the same reason. There were quite exotic ideas, like it would have been cometary impact on Earth, but it has been shown that this idea disagrees quantitatively with the observed parameters. Also, the ideas that it could be geomagnetic or heliospheric crack, so that the shielding of the heliosphere or geomagnetic field on Earth have been reduced for some reason. It doesn't help because still the effect is much smaller than the observed. And after all, it has been agreed that the only possible source of this spike is related to solar energetic particles or some super solar flare. And there have been many confirmations published on that, and we will discuss more about that detail. So what do we know now? After the first discovery 10 years ago, now we have 5 events of this type of extreme solar energetic particle events, as shown here. As you can see, the dates are in the approximate dates of the event are in each bar. They're spread over several millennia. So 5 confirmed events. It's the one I said, which was the first to be discovered, the 993 AD, 660 BC, 5000 BC, and 7000 BC, and 3 candidates which still need confirmation. There are also some other hints, but basically that's the statistic now. 5 events and 3 candidates. And on this plot is shown the strengths of these events in the production of cosmogenic isotopes, comparing to, if you can see this small blue bar on the right, that's the strongest solar-energetic particle events measured during the instrumental era. It was in February 23rd of the year 1956. And you can see that all these extreme events are a factor of 30 to 70 or to 100 stronger than the strongest event we have been observed during the last decades. And the horizontal red line shows the cosmogenic isotope method threshold. So we cannot observe the events smaller than this with cosmogenic isotopes. And even this threshold is the factor of 15 stronger than the strongest directly observed events. And as I said, we can estimate the spectra of these extreme solar-energetic particle events. And this is shown by the upper solid lines with the uncertainties being shaded areas, and dashed lines in the lower part of this plot are strong solar-energetic particle events directly observed during the last decades, including the hard spectrum event, blue, a soft spectrum event, orange, and a typical strong solar-energetic particle event, a blue dashed line. And as you can see, the reconstructed spectra of the extreme events are quite similar to the observed ones, just 170 higher than them. So we may think that these events are similar, just much stronger than the observed one. Just to say a few words about the effects of such an extreme event, this plot shows the radiation effect on the ground from such an extreme event, and it can be up to 100 millisievert in the polar areas, which is strong but not fatal. However, that's because we are very well protected by our thick atmosphere and also the geomagnetic field, as you can see in the mid-latitude and tropical regions. The radiation effect is quite small. But if we rise up and say fly over the 50 kilofeet, then the radiation dose would have been very strong, of more than 1 ziver per hour, if we fly in the polar region. So during strong events, flight should be grounded or rerouted to avoid a fatal dose of radiation in the polar regions. Okay, so now let us put together the entire statistics of solar-energetic particle events as we know now, and on the left-hand side of this plot is shown the occurrence probability function for the known or directly measured events during the space era. And if we try to fit this distribution with the Weibull function, which is quite often used, a gray curve, we may see that it falls down quickly. On the other hand, if we now place the observed extreme solar-energetic particle events as shown by the stars on the right bottom corner of the plot, they form quite a different branch of the distribution, which per se can be fitted by a green curve, which is an exponential, which is quite often appear for this kind of event. On the other hand, we may still fit both both type of events with the same distribution function as shown by the red dashed line. So at the present, just from this plot, we cannot say whether these extreme events based on cosmogenic-proxy are the same type of distribution as the observed event, or do they form a separate type of events which belongs to different distribution. And here I come to the topic which was in the title, Black Swans versus Dragon-kings. Black swans is quite popular term nowadays, and it implies a high impact event which is not expected from the previous empirical knowledge, but can be understood a posteriori. So when it has happened, we can say, oh, of course, we do understand what's there. We just didn't thought about that. And a typical example of that could be, for instance, in the ancient community living somewhere near the hill, where they were living for decades, nothing happened bad, and then a landslide occurs. Then they may think, okay, we understand. There normally it was okay, but then there were heavy rains, which leads to the landslide. So we now know what is the event. We just didn't think of that beforehand. So that's Black Swan, the unexpected event, which can be understood after it does happen. Dragon-king is another type of event. It's a huge impact, totally unexpected event. So king means its size, it's big and it's huge impact, and dragon, it cannot be understood even after it happens. So even if it occurs, we cannot understand it with the present knowledge, and new knowledge needs to be created to understand that. And an event of this type is, for instance, an earthquake, also for the ancient community. So when the earthquake happens, they don't understand what it is and why it comes. It's just something which comes and hits, and you don't know why and where and when. So can we now, coming back to the extreme events, can we now say whether these events are black swans, or basically black swans here, I mean that extreme events are the same type of events of solar energetic particle events as we know from the past decades, just 2 orders of magnitude stronger, but the physics is the same. Or are they dragon-kings, which means that it's something we cannot understand now in the term of the present knowledge. And we need to think of something different, what we don't know yet. The key point here is the so-called weak extreme event, if I'm allowed to say that, which are still an order of magnitude stronger than everything we have observed before, but they would be an order of magnitude weaker than the most extreme of those. Unfortunately, here it's not easy to get information because such events haven't happened yet. So in our instrumental era, and because of the detection threshold, we don't have much chance of getting more statistics here, but we may expect to find maybe a dozen of other events a little bit weaker than the weakest so observed presently. And then we may say whether this is the same distribution or different types of distributions. Another thing is that because of the spectra of the similarity of energy spectra of the extreme events and the observed events, it is quite likely that physics behind is similar. Another thing to check, and I'm quite often asked about this question, is at what level of solar activity do extreme solar particle events occur? That's not very easy to answer, but some answers can be done. Fortunately, we have now full reconstruction of solar cycles for the last millennium, for the last 1,000 years, based on radiocarbon. And in this plot, I show solar cyclic variability in reconstructed sunspot numbers around 3 of the events or candidates. And as you can see, the red curve is the sunspot number reconstructed directly from radiocarbon data, and the blue line is reconstruction when the expected shape of the extreme event has been removed from the data. For instance, in panel A, for the event of the year 993 AD, the production of radiocarbon was so strong during the event that the whole cycle has been distorted. But if we remove this, the effect of the extreme event, then the cycle is nicely reconstructed, and we can see that the event occurred around the maximum of the solar cycle. The same holds for other candidate events. They always occur near the maximum of the cycle, suggesting that probably they are related to the solar activity. If we go to further events, we don't have information of individual solar cycles, but what we can see is that they occur, as shown by green arrows, during periods of mostly moderate solar activity on average, not around very high periods like grand solar maxima, but around the moderate activity period, which is not what we would expect intuitively, but at least not during the grand minimum. So still there is a relation between the extreme events and solar activity. Now I will slightly go to a different direction, and will tell about data from the moon, or cosmogenic isotope from the moon. Moon is not protected by atmosphere or magnetosphere, which means that all energetic particles hit ground or surface of the moon, going deep into the layers. And if we again consider the same pair of cosmic rays as previously, more energetic cosmic ray 1 and less energetic cosmic ray 2, the more energetic can produce a nucleonic cascade inside the lunar soil or rock, producing, in this case, we will discuss about aluminium-26, another cosmogenic isotope, which is not so much present at Earth, but is produced quite a lot in the lunar soil. So the aluminium-26 is produced somewhere at the depth, and it stays there because there is no transport. Less energetic cosmic ray also can produce aluminium-26, but at a shallow depth. Now we take another time, T2, which is much greater than T1, and a similar pair of cosmic ray particles produce similarly aluminium-26, and we see that aluminium-26 produced by cosmic ray 1 at time t1 is located exactly at the same depth as at time t2. But less energetic cosmic rays then produce cosmogenic isotope at shallow depth. So here we have energy resolution. So this is a very simple spectrometer where depth corresponds to the energy of primary cosmic rays, but there is no time resolution because all isotopes produced at different times stay at the same depth. So we have a flux integrated over the time, actually over the lifetime of the isotope. And for aluminium-26, it's around 1 million years. So if we have measurements of the concentration of aluminium-26 in lunar samples as a function of depth, we may roughly reconstruct of the energy spectrum of galactic cosmic rays from the deep part of the samples and solar energetic particles at the shallow depth. And as shown in the left top panel here, this gray curve is the average solar energetic particles spectrum is estimated over the mega year time scale. And the stars and dots show the mean fluxes as we observed during the recent decades from direct measurements, where the red stars correspond to solar cycle 22 to 24, and the blue curve only to solar cycle 24, which is a moderate cycle or typical cycle. The red stars include also cycles 22 and 23, which will still belong to the grand maximum of activity with higher flux of solar energetic particles. And the blue line here depicts the spectrum, the time average spectrum of solar energetic particles if we consider both, if we consider this type of distribution, the red dashed line, so assuming that normal solar energetic particle events and extreme events have the same origin. And as you can see, the agreement is quite well now, which means that considering both direct measurements and extreme events, we now, which are totally independently obtained by different methods, we now much more or less precisely the mega year average flux of solar energetic particles obtained independently from lunar samples. An interesting thing is shown here on the right-hand side panel, which is a cumulative a distribution of the flux of solar energetic particles as function of the time of observations. And as shown here, during the 70 or 100 years of measurements of the flux, as we have now with direct measurement, we actually account only for about half of the long-term average solar energetic particle flux. And this is important to know for the modeling of radiation environment on the long-term scales, in particular for the long-lasting space missions. And another thing is we can look at extreme solar events. We can look not in the past of the sun, but on a big ensemble of sun-like stars, which can be observed now with the modern instrumentation. And this relates to superflares on sun-like stars that have been discovered also 10 years ago in 2012 by another Japanese group led by Maehara-san. And an example is shown here. So on a sun-like star with clear periodicity related to the rotational period of the star, there might be some superflares which have huge energy, so more than several orders of magnitude greater than the flares we observe on the sun. And if we assume that they are produced by the same mechanism as on the sun, so by reconnection in their active regions, we would need to have huge sunspots, as shown in this illustration that would have covered a major fraction of the solar disk. However, it has been estimated that if we consider the present knowledge of how a solar flare occurs, that would lead to the size of sunspot, which is impossible for the sun, since it can hardly be greater than the depth of the convection zone. So the greatest solar flares were observed to be few times 10 to 33 erg, the bolometric energy. And for the sun-like superflares, the greatest energy is 10 to 36 erg, which is beyond the sun's ability in the present knowledge. On this plot is shown again the occurrence probability function of flares on sun and stars. The green dashed line, diagonal one, is the statistics for the solar flares, and the gray shaded area is a projection from sun superflares on sun-like stars. There are several estimates here, but if we put the statistics of extreme solar-energetic particle events from cosmogenic isotope proxy, it's shown here, where of course the translation from the strength of solar-energetic particle event into the bolometric energy is not straightforward, but uncertain, maybe with a factor of 3 or so. Still, we have roughly an order of magnitude, a difference between the energy of sun-like superflares and what we know from extreme solar events, and also the superflares, if projected onto the sun, would occur much more frequent than extreme solar-energetic particle events. And this shows the greatest directly observed solar flare, and this is roughly a theoretical maximum which we expect from the sun, assuming that the mechanism works the same. So I come now to a summary of this talk. What do we know about these events? First, we know that the sun produces extreme events, which are a few orders of magnitude stronger than those during the space era. Very important is that spectra, energy spectra of these events are similar between the extreme events and what we observe directly, which suggests that these are probably black swans, so that we can understand what these events are. Presently, we know 5 events which are listed here, and 3 candidates and a few suggestions. So still, we may expect to get several more events of this time, but most likely the statistics is more or less done. On the other hand, from superflares occurring on the sun-like stars, we know that superflares 3 to 4 orders of magnitude stronger than those observed on the sun can occur, which is incompatible with the present knowledge of the sun. Doesn't mean that these are dragon-kings, because we cannot understand them on if they would have occurred on our sun. Thus, there is an inconsistency between the long-time statistics of extreme solar event found by the cosmogenic-proxy data on Earth and superflare statistics of sun-like stars observed from a big ensemble averaging. This leaves the question open: do we understand the mechanisms? Are we basically speaking of the same type of events? This is still unclear. There are many some possibilities to reconcile and answer this question. And what would that imply for us? Even for this huge event, civilization will survive. And this is obvious because there have been several events of this extreme events during the last millennia, and ancient people didn't even notice that because they are protected by the geomagnetic field and the atmosphere. But now we're different. Consequences would be dramatic for our highly technological civilization. In particular, such an event would lead to instant loss of the spacecraft fleet, maybe except of low orbiting, low inclination satellites, which are protected by the geomagnetic field. But geostationary satellites would be highly likely lost instantly. This also leads to fatal risk for polar jet passengers and crews, and particularly for astronauts, damage to other technological networks. According to estimates, the recovery would take 5 to 10 years, full recovery, and cost huge amount of money. Good news for us is that the events are rare, maybe a few per millennium. So we still have chances to live quietly. Bad news is that they can appear at moderate solar activity level at which we are now. So they're not necessarily related to grand solar maximum, which have been recently, but can be during the moderate solar activity. Just we will see. Thank you for the attention. That's what I wanted to say.
Thank you so much, Ilya. This was a great talk. I'm very glad that you gave this update about the status of what we know about these extreme events. We have already a couple of questions here in the chat. Actually, there are 3 of them that look somewhat similar, so I shall read out loud. These are by Ludwig Klein, Hugh Hudson, and Alexander Graver. So basically, the question is about the correlation between the occurrence of extreme events and solar activity as recorded by sunspots. So, for example, for the 1956 event, Ludwig Klein says that it was a very complex extended active region, and the appearance of such active regions may not be captured by the reconstruction of past activity cycles, which may give something like a temporarily smoother sunspot index. So the contradiction, the correlation between spot and flares is not that obvious. And the related question is, what is the connection to the occurrence of other types of activity like CMEs?
Okay, so I will probably. Okay, can you repeat the first question?
So the first question is there necessarily a one-to-one connection between high levels of solar activity as given by the sunspot number and the occurrence of large flares? And the second question is there a connection with the occurrence of CMEs and other types of solar events?
Okay, for the first question, probably not necessarily one-to-one, but in order to produce this kind of event, we need a large amount of magnetic energy, because this is eventually the source of energy for eruptive events. And so most likely, yes, there is a need for large and most important, very complex active region, so that the magnetic energy can be released probably through the reconnection. About the flare and this event and CME, I would say yes. If we speak of the solar energetic particle, we know the most effective acceleration or the bulk acceleration happen at CME-driven shock, and there are some models showing that probably the most effective acceleration would be if there were two shocks approaching to each other, so two consistent release of CMEs, and they merge closer to each other. On the other hand, there is a geometrical factor. So in order to be an solar energetic particle event to be geo-effective, the parent flare and or CME should appear near the western limb of the sun. If it occurs on the central disk or east limb, that most likely the solar energetic particle event would not be that strong near Earth.
Okay, so Ludwig just added a comment saying that there's no large SCP event without CME or without flare. Thank you for Ludwig for that. Another type of question is the connection to solar analogs. So there were two comments, one by Steve Spangler. He says that with regard to superflares on other stars, one needs to be careful about the degree of similarity. The example you showed had apparently a rotation period of about 15 days, suggesting that it is younger than the sun. So young G-type stars are known to show higher activity. And there was a related question by Bozena, or comment by Bozena Czerny, who says that she's just thinking that these flares happen on fast rotating stars. So this raises the question also about what is the criterion? What do we call solar analog, and the depth of the rotation zone and so on?
Yeah, that's of course very good and expected question. Yes, actually, there were even some works claiming that the sun is not a sun-like star, which sounds weird, but okay, there I will show here again. Yeah, I totally agree that it's not clear what is solar analog or sun-like star. In this plot, we see that the occurrence probability has been updated from the primary estimates is shown here to more recent work by Okamoto et al. Reducing slightly, but still it's not. One can estimate the visible parameters. I mean, temperature, rotational period, even the level of metallicity, but there are parameters which we can hardly estimate, like the depth of the convection zone. And there are even speculation that the shape of the differential rotation may affect the activity of the sun. So yes, there are a lot of uncertainties between the studying of sun-like stars, meant to projecting an ensemble statistic onto the sun, onto a single member of one sun.
So to move on, there's a question by Miriam Hofer, and she's asking, are there some objects or constellations in the solar system that could influence or augment the probability of the production of strong flares? Did you check that?
I'm not quite sure I understood the question. Is it related to some gravitational impact of planets, or?
Well, Miriam, maybe I let you ask the question directly, so you can formulate it in a different way if you wish. If you turn on your mic.
Do you hear me?
Yes.
Yes. Listen, I just guess, I don't know, but somehow must there be a reason for the strong flares? I'm just looking for a reason. Did you see or look about the solar system? How is it built up in these special events? How is it? How are where is Jupiter and where are the other stars? Or do you have another idea of how this can happen? The strong flare itself?
No, we didn't, and frankly, I didn't expect any effect of the planets on Superflare or something like that. But the dates are known. One can check. At least there have been many studies that there is no proven relation between the planet constellation and the level of solar.
Okay. Yeah.
Okay. Does it answer your question? She's muted. Okay. Guillaume already has a comment regarding again this sun solar analog connection. Maybe you can. I'll let you speak up, Guillaume, so you can formulate it, because I'm not sure what you wanted to ask.
Yeah, I hear quite a lot that the sentence that you use, Ilya, about the sun is not a sun-like star, but so maybe I make a bad humor there, but maybe sun-like stars are not sun-like. So who's wrong there? Is it the stellar people who attribute a solar property to remote stars, or is the sun really special?
Well, I think you know the answer, of course, but I mean, I can say that of course sun is a sun-like star by definition, but the thing is, you probably know that if the sun was observed as with the same technique as all the sun-like stars, it would probably not be listed as a sun-like star within this ensemble.
Yeah, so maybe the name of sun-like stars is bad.
Yes, maybe. But yeah, okay. Yes.
Okay, does it answer your question, Guillaume, or your comment, I should say? I guess so. So, well, other questions may come up. I was wondering, with more sensitive equipment and especially regarding new accelerators, what are the prospects of having better constraints? I can imagine that you have more, that you can detect more events. How about the energy spectrum? What do you expect in the next years?
For the energy spectrum, in fact, we are we can only define the hardness of this, the hardness ratio of the spectrum using different isotopes. So it's roughly the ratio of fluence with energy above 200 MeV to that above 600 MeV. And we only can feed, for instance, the known spectra to that, so that all isotopes are fitted more or less precisely with the same spectrum. So it's not non-parametric, it's a parametric reconstruction. So we're just trying to find the most probable values of the parameter. About the AMS, the acceleration mass spectrometry, as you said, it's getting better and better. So we do expect to get more events for the last millennia, which will of course improve statistics. Does it answer?
Yes, indeed. Yes. Okay. So there's a comment by Tom Ayres saying that the sun is not special. There are many similar stars in the solar neighborhood. Even Alpha Centauri A can be quite nearby. So I guess there should be another talk about what we mean by some solar analog, solar similar, sun-like stars.
But I am not a deep expert in that field.
But it's good to know, so that gives an idea for the future. So Brigitte Schmiede has a question. Do you have an idea that in space all the events are much weaker, even weaker and weaker? Maybe I'll let you speak up, Brigitte, because so that you can specify.
Yes, in the past, the events were much more important and look by a factor 70 or even more 1,000, and now they are weak and weak, and even GLE, it's very small and rare. So do you know if it is a question of rotation of the sun or what is your idea?
Yeah, thank you, Ajit. I don't think it's related to the rotation of the sun, because we are speaking of time scales of tens or thousands of years. That doesn't affect the rotation of the sun much. I think the size of the recent events becoming smaller, that's related to the overall decrease of solar activity level from grand maximum, which peaked during the solar cycle 19 to the present moderate cycles, and we clearly see that in the strengths of events and specifically at GLEs. But for these extreme events, as I said, they typically occur during the moderate solar activity. So we don't know if whether this is just a purely statistical coincidence of several favorable factors which make this extremely strong event, or what is that?
Okay. So there's another comment by Ludwig Klein, who is very active tonight on the chat. He's saying that the 20 January 2005 GLE occurred in a rather weak solar cycle. So this comes back to the earlier point you mentioned. So it just means that these events are rare.
Yeah, it also occurs quite late in a solar cycle, and specifically and especially GLE number 70, which was in December 2006, was actually near the minimum. But yes, it just took place.
Okay. A quick question of mine. You said before that you could sort of distinguish between the cause, whether it was solar or gamma ray burst, by looking at the hemispheric symmetry, I mean, in ice cores, I guess.
Yes.
How is that? It's not very really clear to me.
Well, since gamma ray burst or supernova is a point source, it illuminates Earth from one
Yes.
hemisphere or even less than that.
Yes.
If it was one event, okay, it may occur near the equator, so that both Earth hemispheres are illuminated.
Yeah, so it can be anywhere. Actually.
Yeah, and there is almost no crosstalk between the hemispheres in the Earth atmosphere. So if everything is produced in northern hemisphere, you don't expect to see strong signal in the south hemisphere. But now we have several events of that kind, and all are symmetric, which means that it's very unlikely to be a point source. It was really a global phenomenon.
Okay, I see. Yeah.
But a stronger argument against gamma ray source is that there is a significant amount of beryllium-10 detected, which is not produced by gamma rays.
Okay. So I think I take two last questions. So one again by Guillaume, I think I missed the point earlier, is that whether one extreme event could not be actually a series of events that took place within a narrow time window.
Yes, thank you. This is this is good question indeed. It could. So when we speak of extreme event, it can easily be a sequence of events like it was in the fall 1989 or 2003. But we are quite certain that the duration of these events was not longer than several months. So it cannot be several years in a row. It was shorter than a year because using, for instance, trees with different growing seasons from different hemispheres, we can point out the dates or the time of events with accuracy of few months.
Okay. And in that case, I'll take the last question again by Miriam Hofer. She's asking whether you checked the size and distribution of coronal holes just before and after the more recent events.
If we still speak of extreme events, then of course no, because we have no idea what was the coronal holes during that events. The most recent was a millennium ago. But for others, for GLE events, of course.
Yes, the GLE events, I guess.
Yeah. Okay. For GLE events, yes, of course. It's all. But they are not directly related to coronal holes. They are mostly flares and or seams.
Yeah, there should not be an obvious connection. Yeah, okay. Okay, let's move on. I think we will stop here. Thank you again very much, Ilya, for this nice and enlightening talk. Thank you also to all the attendees, especially US citizens who are preparing Thanksgiving, and those who are working with Solar Orbiter because they are the Solar Orbiter meetings at the same time, unfortunately. I just take the opportunity to mention that next week we will have a talk on a completely different topic by Annika Seppele on the connection between solar variability and climate. And again, like for all of these webinars, you can find them on the website of EC, so you can listen again to them if you are interested. With that, I wish you a very nice day or evening, depending on where you are, and hopefully see you soon again for another webinar. And many thanks again to you, Ilya.
Okay, thank you for invitation and for attention to those who